So let's start with that. In this class, I will be covering a Pelton turbine, what is the effective head of this particular type of turbine, what are the various efficiencies involved in the analysis of Pelton turbine, and also the design procedure. I will be also solving one design problem related to Pelton turbine. Let's go ahead with that. So this is a normal layout of a dam. Let's see what are these things. This is the head race. This is the potential head of the river at the dam side. This is the tail race. It is the potential head of the river at the turbine side. And if you see the difference between the head race and tail race is known as gross head. Okay. Now, if you see, this is the height above which our Pelton turbine is installed. And if you see when the water start moving from penstock through various fittings and through nozzle when it gets striking all the blades of the Pelton turbine, throughout this path it passes through various pipe fittings and also through a closed conduit. So because of that, friction losses and various types of other minor losses are involved, which may be collectively taken as HF. So with this, all of this thing in your mind, the effective head for the Pelton turbine would come out to be gross head minus the height above the tail race minus the losses due to majorly friction and also including other minor losses. Let's talk about the various efficiencies involved while we are analyzing the Pelton turbine. We start with water power, which is the energy at the dam side. It converted into kinetic energy through penstock and at the end getting converted in a very high velocity jet with the help of a nozzle. Here two things are involved. First, the flow rate, and second, the nozzle efficiency. The ratio of the two, kinetic energy to the water power, is the nozzle efficiency, and flow rate involved is the total flow rate coming out of the nozzle. Now, when it's converted into runner power with the help of the Pelton runner, what happens? First of all, there is a leakage happening, and because of that, volumetric efficiency comes into the picture. It is the ratio of actual flow rate to the total flow rate. And also, because there is a hydraulic conversion, there is also hydraulic efficiency which will come into picture, which is nothing but runner power to the kinetic energy. Once the runner power, we achieve power at the runner. On the runner, it is installed on a shaft, and we found that by the rotation of the runner, we get a rotation on the shaft, and this shaft power can be utilized for any mechanical work. But whenever we use the shaft power, we need a coupling or a bearing, whether it is a floor mill or a generator or anything. So the shaft power available at the shaft will not be what we have at the runner. Because of this mechanical coupling and all, there will be some losses which involves mechanical efficiency, which is the ratio of shaft power to the runner power. Let's say, which is very common in the hydropower generation, we have a generator. So we get a generator installed on our shaft and we are getting a generator power. Again, the efficiency involved will be the generator efficiency. So let's see all this thing one by one. Water power is rho g QH. Kinetic energy at the turbine applied half rho q V1 square. Leakage Q minus Q dash. Runner power rho, now it is Q dash because there is a leakage loss V1 minus U1 plus cos theta. Shaft power is what we are going to get at the shaft, and last is the generator power. So let's move ahead and talk about the designing of a Pelton turbine. The following points need consideration while designing a Pelton turbine. First is the velocity ratio. So when we see a theoretical conversion from potential energy to the kinetic energy, this is what we get. And we all know it from our high school knowledge as well. Velocity theoretical is under root 2gh. But actually, because of the nozzle conversion, there is a loss happening. And that loss is represented by a velocity ratio, which is the actual velocity to theoretical velocity, which is also known as velocity coefficient CV. And for designing a very efficient Pelton turbine, this CV should range from 0.97 to 0.99. Similarly, there will be a speed ratio involved, which is known as CU, which is the ratio of blade velocity to the theoretical velocity. And for an efficient design of a Pelton turbine, this CU should range from 0.45 to 0.47. Mean diameter of the wheel, which is also known as pitch circle diameter, is uh, given by velocity of the blade, which is u, which we have just calculated above, into pi is equal to pi dn by 60. Let's see. This d is either a mean diameter or a pitch circle diameter. You can see it in this figure. This is what we have. A pitch circle diameter is like this. This is what we have. Now, if you move further, jet ratio. What is jet ratio? It is a ratio of the mean bucket diameter, a pitch circle diameter, to the diameter of the jet. For an efficient Pelton turbine design, your M should lie between 11 to 15. However, if no information is given, it is always recommended to take the value of M equals to 12. Let's move further. So if you continue designing, there is one more aspect come, how many jets we use for our Pelton turbines. So theoretically, a maximum of 6 jet can be fitted. Practically 2 when the runner is vertical and 4 when the runner is horizontal. How this number of jet comes into picture? When we talk about the flow rate hitting the Pelton turbine, this flow rate is nothing but pi by 4 d1 square, which is the area of the nozzle outlet into the velocity of the jet, and multiplied by n. This n here is the number of jet involved. This is very crucial while designing any Pelton turbine. Let's see this. This is what we have. This is our Pelton runner, and these are the jets hitting our runner. Moving further, if you talk about the blade itself, working proportions, there will be an axial width B, there will be a radial length L, and there will be a depth T. These all are represented in the terms of jet diameter, and there is a range prescribed for each of these proportions. This D is the diameter of the jet, and let's see the blade. This is how we can see the blade of a Pelton turbine, and all these proportions are there. Let's move further. Last but most important, how many number of blades, which is popularly called buckets in case of Pelton turbine, we will have it. There are two very popular empirical formulas available. First is Z is equals to m by 2 plus 15, where m is again the jet ratio, which normally we take it as 12, and also one more 5.4 into under root n. So you can use any one of these two.